Have you ever just stopped to think about what happens when you click on a link? I mean, really think about it. 1 second, you're looking at one thing, and a literal split second later, a whole new web page from halfway across the world just appears. It feels like straight-up magic, right? Well, it's not, but it is one of the most brilliant and resilient systems ever created by humans. And today, we're going to pull back that curtain.
So what's really going on there? How does your request for, say, a cat video travel across cities, countries, and oceans, find the exact right server, and get a response back to you in the blink of an eye? To figure this out, we're going to do something cool. We're going to follow a single, tiny piece of your request on its incredible journey across the internet. Let's do this.
All right, to wrap our heads around all this, we're going to need a good analogy. And the best one is this. Think of the entire internet as a massive, super efficient, global postal service. Every single thing you do online, every click, every search, is like sending a package through this system. Seriously, if you can picture this digital postal service, the rest of the journey will just click into place.
So here's the first surprise. Your request isn't sent as one big letter. No way. First, your browser writes the letter, which is called an HTTP GET request. But then, a protocol called TCP, think of it as a hyper-efficient shipping clerk, comes in and chops that letter up into a bunch of smaller, numbered postcards. Each one of these postcards, or segments, also gets a port number, which is basically like writing "Attention, Sales Department" or "Apartment 4B" on the envelope. For a standard web page, that door number is almost always port 80.
Now, our digital postal service has options, just like the real one. For a web page to load correctly, every single one of those postcards has to arrive in perfect order. That's why we use TCP. Think of it as certified mail with tracking and delivery confirmation. It keeps an eye on every single piece, and if one gets lost, it sends a replacement. The other option, UDP, is more like a regular postcard. You just drop it in the mail and hope for the best. It's way faster, which is great for things like video streaming or online games, but for our web page request, we need the guaranteed delivery that only TCP can provide.
Okay, this next part is super clever. It's a process called encapsulation, which is really just a fancy word for wrapping things in layers, kind of like a Russian nesting doll. So you take one of our postcards, the TCP segment, and you put it inside an envelope. That's called an IP packet. This is the main package with a final destination address on it. But then you take that whole envelope and put it inside a local courier box, which we call an Ethernet frame. This box is only for the very next stop on the journey.
All right, pay close attention because this is probably the biggest aha moment in understanding how the internet works. Every package has two addresses on it. The first is the IP address. That's the final global destination, the full street address of the server, maybe in another country. That address never ever changes during the trip. But the second address, the MAC address, is the address of just the very next stop on the line, like the next local post office. And here's the kicker. That MAC address gets ripped off and replaced at every single stop along the way.
So who's making all these decisions? Who's in charge? That would be the router. Your home router is what's called your default gateway, and it's the very first digital post office your packet visits. The router has one main job: to look at the final IP address on the envelope, check its big map of the internet, its routing table, and figure out the absolute best next stop to send the packet to.
Let's see this in action. Your computer is smart. It knows the web server is millions of miles away, so it can't just shout the request into the void. Instead, it takes that IP packet, puts it in that local delivery box, the Ethernet frame, and addresses it specifically to the MAC address of your home router. And just like that, the first leg of this epic journey has begun. A tiny trip from your computer to that little box with the blinking lights. Okay, now the router has the package, and this is where the real magic happens. It immediately rips open that local courier box, the frame, and just throws it away. It's done its job. Now the router is holding the main envelope with that final destination IP address. It consults its routing table and says, aha, to get there, the next best place to send this is to that router over there. So it grabs a brand new box, a new frame, puts the original envelope inside, and addresses it to the MAC address of that next router.
And that's the whole game, right there. This process, unwrap, read, rewrap, forward, happens again and again and again. The packet is literally hopping from router to router across your service provider's network and onto the massive internet backbone. And at every single hop, that outer local address is new, but the inner envelope with the final destination, it stays perfectly intact, just getting a little bit closer with every leap.
Finally, after all those hops, it arrives.
The web server gets hit with all these little numbered postcards, and because of those TCP sequence numbers, it knows exactly how to put them back together in the right order to read your original request. It gets the message loud and clear. And then it does the exact same thing, but in reverse. It chops up the web page into a bunch of new postcards, wraps them all up, and sends them on that same incredible hop-by-hop journey right back to you. So, let's just recap. What feels like magic is actually just a brilliant, layered system of rules. The key things to remember are data gets chopped up and wrapped in layers. Every piece has two addresses, the permanent global IP address for the end of the line, and a temporary local MAC address for the very next step. Routers are the digital post offices, making one smart decision at a time. And good old TCP is the certified mailman, making sure everything gets there safely. It's not magic, it's just an incredibly scalable and fault-tolerant design. And that leaves us with a final thought to chew on. This entire system, this idea of packet switching, was born out of the ARPANET project. It was literally designed with the goal of creating a communication network that could survive a nuclear war. It was built for absolute resilience. But now, as we're charging into an age of AI, the metaverse, and data demands they couldn't have even dreamed of back then, how does this Cold War-era architecture evolve to handle that future? It really makes you wonder, doesn't it?